So in this video we will look at how to sketch cubic graphs, and before we get started, just to remind you on how to do mathematics. So number and copy the examples, ask your tutor or teacher if there are any steps that you do not understand, number the questions, and unless you have the ability to get fit while watching someone else run, you must do the questions on your own before watching the answers. Mark your answers if it is incorrect, write down the corrections, and make sure you understand where you went wrong. This will enable you to do better the next time you attempt a similar sum. So an overview of what we'll be doing in this video is we will first look at when we're given an equation of a graph and how to sketch it from the equation, and then when we're given a combination of information. So to start off, if I am given a cubic graph in the form of ax to the power 3 plus bx squared plus cx plus d, what defines a cubic graph is basically that the highest power is to the power of 3, and then the variables a, b, c, and d all represents numbers. So the steps we're going to follow, the first thing we do is we look for intercepts. So we have both y-intercepts and x-intercepts. So to find the x-intercepts, we basically set y equal to 0 and solve for x. And then similarly, to find the y-intercept, we set x equals to 0 and solve for y. And then we can plot them on the graph once we have solved for them. Then we look for the coordinates of the turning points. So for the turning points, we need to find the x values by first solving for the first derivative and put it equal to 0. And to get the y values, we simply substitute the x values into the original function. So then we can find our coordinates of the turning points and we plot it on the graph. Thirdly, we're going to look at the point of inflection. Now to find the point of inflection, we need the second derivative. So to find the x values, we solve for the second derivative equal to 0. And then once again, if you want the y values, you obviously just substitute your x values into your original function, and that would give you your coordinates of the point of inflection. Right, and then we need the shape of the graph. Now we can already see more or less what the shape will be, but just to confirm that, if the value of a, if this a value is greater than 0, or if it's positive, then the graph will end with a positive end. The concavity will be positive. But if the a value is less than 0 or negative, the graph will end like that, or the shape will look like that. Now, after you found the shape, you can basically connect the dots and then you can draw your graph. Always remember also to name your intercepts, especially if they ask for it, to name the intercepts, and also if they ask to give you to give the point of the turning points, also to name them by giving their specific coordinates. Okay, so let's look at a practical example. It says sketch the graph of fx showing the intercepts with the axis, the coordinates of any stationary points, and the coordinates of the point of inflection. So here they specifically ask for the intercepts, the stationary points, and the point of inflection. If you don't name those, then you can lose marks. Alright, so with these, what I'm going to do is I'm going to follow through all the steps that we just saw previously, but I'm not going to go into detail on factorizing, and also when substituting in a value. I'm not going to go into detail with that. If you need to know how to factorize, just go to one of the videos that helps you to factorize cubic functions and also to solve for them. Alright, so if I have fx equal to negative x to the power 3 minus x squared plus 8x plus 12. The first thing I can do is obviously I need my intercepts. So to find the intercepts, I need my x-intercepts. Right, and to find my x-intercepts, I need to put y equal to 0. So that means I need all of this equal to 0. So we have minus x cubed minus x squared plus 8x plus 12 equal to 0. Now, if I factorize this, which I said I'm not going to do into detail, but if I do factorize this, I get negative and then x plus 2 x minus 3, and then x plus 2 again equal to 0. Okay, so that means that my x-intercepts lie at x equal to minus 2 and x equal to 3 and x equal to minus 2 again. Alright, so that actually means that the turning points one of the turning point lies on x equals to minus 2. Alright, so once I've got that, I can plot them here. Remember to name them. So this one would be at minus 2 and this one would be at 3. Right, so the next thing we want to do is to get the y-intercept. And to get the y-intercept, I need to say x equal to 0. Now, the y-intercept you can actually always read off from the graph, because this constant value here is always your y-intercept. And you can see that even if you follow the steps by putting x equal to 0, all of these terms will fall away and you'll just be left with that constant over there. So at y equals to positive 12, that's where your y-intercept is. So we can plot it on the graph and we can name it as 12. Okay, so next up, we found our intercepts. Next step is to find the turning points. Okay, so I'm just going to use this space over here. So turning point. And to find the turning points, I need to say the first derivative equal to 0. So my first derivative of this is negative 3x squared minus 2x plus 8 equal to 0. And once again, I'm not going to go into detail about factorizing this, but the factors, when I factorize it, is x plus 2 and 3x minus 4 equal to 0. Okay, so that means turning points, the x values of the turning points are at x equals to minus 2 and at x equals to 4 over 3. So what are my y? Because remember, you need to find the coordinates of the turning points. So the y values, if I substitute it into the original graph, so if I substitute in negative 2 into this original graph over here, then I'll be left, then I get 0. And if I substitute in 4 over 3 into my original graph, I get 500 over 27. Alright, so now we have the coordinates of our turning points. So the one is here at minus 2, so that one's coordinate is going to be minus 2 and 0. And this one's coordinate will then be 4 over 3 and 500 over 27. Okay, so next we need to find the point of inflection. So the point of inflection is going to is when I set the second derivative equal to 0 and solve. So my second derivative is if I take my first derivative and derive it again, I get negative 6x minus 2 equals to 0. And then if I solve for x there, I get x is equal to 1 over 3. And then if I substitute in 1 over 3 into my original equation, that then gives me 250 over 27. So my coordinate then here will then be 1 over 3 and 250 over 27. Okay, so finally I can just say the shape. I know the shape since the graph, the a value is negative. I know my graph will end negative, so my graph will look something like that. So I can now follow through that it starts like this and then it goes through those points. So that is what the graph then will look like. Right, so for question 28.1, if we sketch the graph of fx showing the intercepts with the axes, the coordinates of any stationary points, and the coordinates of the point of inflection. the first thing we want to find, if I just write down my graph as fx equal to negative x cubed plus 5x squared plus 8x minus 12, right? Then the intercepts is first. So let's get the x-intercepts. And the x-intercepts is by saying y equal to 0 and solving for x. So we're setting this equal to 0. And then factorizing and solving. So if you factorize this, what you'll get is negative x minus 1, and then x minus 6, and then x plus 2. Which then means that my x-intercepts are at x equal to 1, or x equal to 6, or x equal to minus 2. Okay, so if I plot that on the graph, we can see that this would then be at negative 2, this one would then be at 1, and that one would be at 6. Now to find the y-intercept, we need to put x equal to 0, and we can immediately see that my y-intercept would be at y equal to negative 12, so I can plot that on the graph. So I'm just putting this at negative 12 over here. All right, and then we can find the turning points. So turning points is next. And turning points we find by finding the first derivative and equaling it to 0. So my first derivative of this, of my function here, is negative 3x squared plus 10x plus 8 equal to 0. And if I factorize that, I get 3x plus 2 and x minus 4 equal to 0. Alright, so that means x equals to negative 2 over 3, and x equals to 4 is my x values for my turning points. To find the y values, I have to substitute these values into the original graph. And if I do that, I get negative 400 over 27. And over here, if I substitute in 4, I will get 36. Right, so I can plot those on the graph. This one would then be at negative 2 over 3 and negative 400 over 27. And then over here, this top one would be 4 and 36. Okay, and the final thing we need to find is the point of inflection. And that we do by finding the second derivative and solving for x. So my second derivative is if I take this function and derive it again, I get negative 6x plus 10 equal to 0. Right? And then if I solve for x, I get 5 over 3. And if I substitute in the 5 over 3 into my function, then I get 286 over 27. All right, now we can plot that one. So that one is here, and if you need to find where to plot it, obviously just convert your fraction to a decimal, then it's easier to see between which two values that lie. So we've got 5 over 3 and 286 over 27. Okay, and then finally the shape of the graph would again, it's a negative value for a, so it ends negative, so it would be in this shape, right? So then if we follow through with the points that we just plotted, the graph would look as follows. Then for question 28.2, sketch the following graph. So once again, I'm just going to write down the graph. So we've got x to the power 3 minus 4x squared minus 11x plus 30. All right, so we need to find the x-intercepts, and we do that by putting y equal to 0. So x cubed minus 4x squared minus 11x plus 30 equal to 0. Now if I factorize that, I get x minus 2 and x minus 5 and x plus 3. Make sure that you understand how to factorize it. Once again, if you don't, just go and revise that. Okay, so this is then at x equals to 2, or at x equals to 5, or at x equal to negative 3. All right, so if I plot these values, then we have minus 3 over here, we have 2, and we have 5. Okay, next up we need the y-intercept, and we get that by setting x equal to 0, and then y will be equal to 30, so it's going to intercept at 30. So I can plot it over there. This is at 30. And then next we need to find the turning points. So turning points, we have to set the second or the first derivative equal to 0 and solve. Okay, so the first derivative is then going to be 3x squared minus 8x minus 11 equal to 0. If I factorize that, then I get 3x minus 11 and x plus 1. And therefore, my x values are at x equal to 11 over 3, or x is equal to negative 1. Okay, so to find my y values, I substitute those values into the original graph, and that would then give me negative 400 over 27. And on this side, if I substitute in negative 1, I get 36. Okay, now once again, we can plot those coordinates. Over here, we have negative 1. So here we have negative 1 and 36. And over here, we have 11 over 3 and negative 400 over 27. Okay, so those are in. Final thing to do is our point of inflection, and that is by putting the second derivative equal to 0 and solving. So my second derivative, if I derive this one again, we get 6x minus 8 equal to 0. So x is then equal to 4 over 3. So if I substitute this in, I will get 4 over 3 substituted in, and that would give us 286 over 27. Right, so if I plot that, we have this point over here, and this is then 4 over 3 and 286 over 27. Right, and then finally for the shape of the graph, we can see that it is a positive a value, meaning it would end positive. So if I follow through on the points, then the graph would look something like that. Right, so for question 28.3, sketch the graph of fx. We have fx equals to x to the power 3 minus 5x squared plus 7x minus 3. First thing, we need our x-intercepts, and to do that we need to put fx equal to 0 and solve, or y equal to 0 and solve. So we've got x cubed minus 5x plus 7x minus 3 equal to 0. And if I factorize that, I get x minus 1, x minus 3, and again x minus 1 equal to 0. So that means that at x equals to 1 and at x equal to 3, that's where my intercepts lie. So if I plot that, I've got 1 and 3. Alright, so next we need to find the y-intercept, and that we do by setting x equal to 0, so y is equal to -3. Then I put that on my graph at -3. Alright, next up we need to find the turning points, and the turning points we find by finding the first derivative and equaling it to 0. So my first derivative is 3x squared minus 10x plus 7 equal to 0. And if I factorize that, I get x minus 1 and 3x minus 7 equal to 0. Okay, so x is equal to 1 and x is equal to 7 over 3. Then we substitute it into the original equation to get the coordinates. If I substitute in 1, I get 0. And if I substitute in 7 over 3, then I get negative 32 over 27. Right, so then plotting those points, they would lie over here as the 1, the 7 over 3, and negative 32 over 27. Okay, so there's my 1 point, and this is my other point, the one that has 1 and 0 as the other turning point. Then we need the point of inflection, and that we get by setting the second derivative equal to 0, and the second derivative is 6x minus 10. Okay, and then equal it to 0. So x is then equal to 5 over 6, or yeah, I think that's 5 over 3. Yes, and then if we substitute in 5 over 3, this would then be equal to negative 16 over 27. Right, so then if I plot the point of inflection, it lies over here. So the coordinates is then 5 over 3 and negative 16 over 27. Right, so if I then find the shape of the graph, the shape is a positive, it ends positive since the a value is positive. So this is what the shape would look like. So if I follow through on these points, then my graph looks as follows. Right, so sketch the following graph. So in this example, we have fx equals to 5x cubed plus 21x squared minus 9x minus 62. And we have to show the intercepts with the axes, the coordinates of any stationary points, and the coordinates of the point of inflection. So the first thing we need to do is find the x-intercept, and to do that we need to put y equal to 0. So we have 5x to the power 3 plus 21x squared minus 9x minus 62 equal to 0. And then if I am going to factorize that, then I find that its factors looks as follows, where we have x plus 2, and here we have 5x squared plus 11x minus 31. So this second factor can't factorize. So if we use the quadratic formula, then we find that the intercepts here for x equals to minus 2, that's quite easy, but the x-intercepts for this one will be at x equal to 1,62 and x equals to negative 3,82. Okay, so if I plot that on the graph, then we have negative 3, so just to write quite small, negative 3,82, and then over here we have negative 2, and over here we'll have 1,62. Alright, so that's done. Now we need to find the y-intercept, and that we simply do by setting x equal to 0 and solving, and then we get y equals to negative 62. Plotting that on the graph, we get negative, over here, negative 62. Okay, and then next we need to find the turning points. And the turning points we saw is just finding the first derivative and solving. So the first derivative over here is 15x squared plus 42x minus 9, and setting that equal to 0. So now when I factorize, I'll get 3x plus 9 and 5x minus 1 equal to 0. So solving for x, we get x is equal to negative 3, or x is equal to 0,2, or 1 over 5. Alright, so now if I substitute this in, I get negative 3 substituted into the original function, I get 19. And when I substitute in 1 over 5 into my original function to get the coordinates, I get negative 62,92. Right, and then to plot those points, the one point lies more or less over here. So this is the negative 3 and 19, where that lies. And then the other one down here, so that is going to be 1 over 5 and negative 62,92. Okay, so that's the coordinates of this point right over there. Okay, so now all we still need to do is to find the point of inflection and then the shape. So the point of inflection, we know we need to find the second derivative and equal it to 0. So second derivative is then going to be 30x plus 42 equal to 0. So x is then going to be equal to 21 over 15 if I simplify that. And then to get the coordinates, I substituted into the original graph. So I've got 21 over 15 substituted into my original graph, gives me an answer of negative 549 over 25. Right, and then the shape, since the a value is positive, our shape will end positive, so that's what our shape will look like. Now just to plot the point of inflection over here, we have it lying over there, and then we've got 21 over 15 for the x value and negative 549 over 25 for the y value. And then if we follow the dots using that given shape, then our graph would look something like that. Now for question 29.1, we need to sketch the following graph. So here we have fx equal to 3x minus x to the power of 3. So first of all, as we usually do, we want to find the x-intercept first, the x-intercepts, and we do that by setting y equal to 0. So we've got 3x minus x cubed equal to 0. And then obviously if we factorize that, this is quite easy. We just take out a common factor of x, then we get 3 minus x squared, that's left, equal to 0. And if we solve for these two, we can get that x is equal to 0 and x is equal to plus or minus the square root of 3. Right, and then we plot those on the graph. So here we have the negative square root of 3. Here we'll have the positive square root of 3, and there we have our 0. And then to find the y-intercept, we just set x equals 0, and then we'll find if all of this, if we substitute in 0 here, we'll see that y-intercept is at y equals to 0. So this is also our y-intercept over here. Right, and then our turning points, that is where we take the first derivative of the graph and equal it to 0. So the first derivative of this graph is 3 minus 3x squared equal to 0. Now to solve for this, I can just take the 3 over to the other side. We've got 3x, I'm just going to say this is 3x squared equals to 3. When I took this 3 over to the other side, it became negative. Then I just divided both sides with a negative. And then we get, dividing both sides with 3 and then taking the square root, we get that x is equal to plus or minus 1. All right, so our turning points are at plus or minus 1. So substituting that into the original graph, if I substitute in 1 into the original graph, then I get 2. And if I substitute in negative 1 into my original graph, I get negative 2. So my 2 points then lie here at 1 and 2, and the other point would lie at minus 1 and minus 2. Okay, and then our point of inflection would then be, so the next thing we need to find is the point of inflection. So that's the second derivative equal to 0. And the second derivative is, this then becomes negative 6x equal to 0. Solving for x, we just get x equal to 0. So that then, this point over here is also our point of inflection. Okay, and then finally, the shape, we can actually already draw it with what we have. The shape, this is your coefficient, this is your a value, the coefficient of x cubed. So the shape would actually end negative. So if I follow through on the points that we have, we can see that our function looks as follows. Right, so now for question 29.2, we need to sketch fx equal to x cubed minus 3x squared plus 3x minus 2. And the first thing we need to find is the x intercepts. So that's where y equals to 0. So I'm going to say x to the power 3 minus 3x squared plus 3x minus 2 equal to 0. And if I factorize that, I can see that x minus 2 is a factor. So x minus 2. And the other factor that is left is x squared minus x plus 1 equal to 0. Alright, so now this one can't factorize, so we'll have to use a quadratic formula to find the roots there. So x is equal to 2, or then using the quadratic formula, we'll see that x would be, there would be actually no solution for this values. X would be, or we'll get, if we use the quadratic formula, we'll get x equals to 1 plus or minus square root of negative 3 over 2, and therefore it would have no solution because we've got a negative in a square root. Okay, so the only intercept we have is this one here at x equals to 2. We can plot that one. And for the y-intercept, we set x equals to 0, and that is just at y equal to negative 2. So we plot that one at minus 2. Then we need to find the turning points. So turning points, we need to find the first derivative and equal it to 0. We then get 3x squared minus 6x plus 3. Right, so equaling that to 0 and solving. If I solve for that, first thing I want to do before I solve, I can simplify this by dividing everything by 3. I get x squared minus 2x plus 1 equal to 0. And if I factorize that, I get x minus 1 and x minus 1 equal to 0. So in this case, we only have x equal to 1 as turning point. So this is kind of a special type of graph where both turning points are at x equal to 1. Where is our point of inflection? So for our point of inflection, we have to get the second derivative and equal it to 0. So my second derivative, if I take this, is 6x minus 6 equal to 0. So that also gives me x equals to 1. So both my turning points and my point of inflection lie on the same point. So let's just see what my y value is, because I need to plot the coordinates there. If I substitute in 1 into my original graph, then I get -1. So to plot that point, it lies here. So you've got 1 and -1. Now, the shape of the graph in this case is quite important because we need to kind of make out what's happening here. Now, the shape is then going to be, since our A value is positive, it's going to end positive. So it's going to look like this. But this graph in particular is actually, we're going up, and then it's just going to make a slight turn here at the point of inflection and then go up again. So this is basically how you would draw it in this case. Right, so now for question 29.3. In this case, we need to sketch fx, which is equal to x to the power 3 plus x squared minus x minus 10. Okay, normal steps, x-intercepts. So x-intercepts, we need to find y equal to 0, or set y equal to 0. So you have x to the power 3 plus x squared minus x minus 10, and equal that to 0. Then to factorize, we have x minus 2, and then x squared plus 3x plus 5 equal to 0. Now this one can't be factorized, so to find our roots, we're going to equal it, or we're going to use the quadratic. We're going to use the quadratic formula, and here we get x equal to 2, which is quite easy. But over here, when I put it into the quadratic formula, what comes out is x equal to 3 plus or minus. Then we get 9 minus 20, which gives us -11 over 2. So once again here we don't get a real solution, so there is no solution there. And that means we only have, once again, one intercept, one y-intercept, one x-intercept. So for my y-intercept, I will set x equal to 0, and then we get y equals to -10. Alright, so plotting these, we have our 2 over here, and then we have our y-intercept, which is at -10. Alright, now for our turning points. Turning points, we set the first derivative equal to 0. So first derivative is 3x squared plus 2x minus 1 equal to 0. And if I factorize that, what I get is 3x minus 1, and I also get x plus 1 equals to 0. So x is equal to 1 over 3, or x is equal to -1. Alright, so substituting those values into the original graph, this then gives me -275 over 27, and substituting in -1, I get -9. Okay, so now I can easily plot those. We have this one at -1 and -9, and then this guy here, which is now hidden, but it's over here, is at -1 over 3, or 1 over 3, just 1 over 3, and -275 over 27. Okay. Alright, so now we've got our two turning points here, our y-intercept and our x-intercept. We need our points of inflection, and that is by setting the second derivative equal to 0 and solving. So my second derivative is 6x plus 2 equal to 0, and that makes my x equal to -1 over 3. That's then my x value, so substitute it into my original graph or function. That would give me -259 over 27. Right, so plotting that, it's over here, and we have negative 1 over 3 and negative 259 over 27. Okay, so here we have now for the shape as well. Since this is a positive graph, it's going to end positive. So we have the shape looking like that. And here we have the 4 points lying here and 1 point over there. So it means we need to start, if the shape looks like this, we need to start here at the bottom. So the graph is going to come from here, not from there. So that's one thing we know. It comes from here. Then this is going to be, this was our turning point over here. So that's where it kind of turns. That's the point of inflection, our intercept. And then it turns again here at this point and goes up. All right. So that is what the graph then looks like. Okay. So that is when we're given an equation of a graph. Next, let's look at a combination of information when sketching a graph. Now, for example 30, it says a cubic function f has the following properties. F of a half is equal to f of 3 and is equal to f of negative 1 is equal to 0. Then the first derivative of x is equal to the first derivative of at negative 1 over 3 is equal to 0. And then it says f decreases for x between these two values only. And draw a possible sketch graph of f. Clearly indicates the x-coordinates of the turning points and all the x-intercepts. Now, before we get started, let's remind ourselves what does our fx values represent when it's equal to 0, the normal graph equal to 0, then the first derivative and the second derivative. So if I say if I said fx equals to 0, what does that give me? That gives me my intercepts, actually my x-intercepts to be exact. And then if I have the first derivative equal to 0 and I solve for x, I get my turning points. And if I have the second derivative and I equal it to 0, I get my point of inflection. All right, so in this pieces of information that we're given, from this we can see that the graph, when x is a half, 3 and minus 1, the graph is equal to 0. So for those x values, those are our x-intercepts. So from this information, we know that the x-intercepts of our graph will be at x equals to a half, or x equals to 3, or x equals to negative 1. Okay, so those are the pieces of information that we have already, which we can plot on the graph so long. Now I'm just going to draw this graph, and let's say it goes 1, 2, 3 this way, and then 1, 2, 3 this way. Okay, so our x-intercepts, we know that the graph goes through negative 1, so that's over there. It also goes through 3 and a half, so it goes through there and it goes through here. All right, so that's our 3 x-intercepts. Next thing we are given is that the first derivative at negative 1 over 3 is equal to 0. So therefore we know that the turning point, or one of the turning points, we're only given information about one of the turning points. The one of the turning points is at x equals to negative 1 over 3. Okay, so that's all we know. We just know that the turning point is more or less over here. We don't know yet if it lies above the x-axis or below the x-axis. Now, the next thing that they tell us is f decreases for x being an element of negative 1 over 3 and 2. So over here, now remember the graph can either look like this or it can look like this. So if it says that it decreases from negative 1 over 3 to 2, we just saw that one of the turning points is at negative 1 over 3. That means from this turning point down to this turning point, this form decreases. But this form, from this turning point to this turning point, it's actually increasing. So therefore, we know the first shape is the shape that we're looking at. So I know that now that my turning point here lies somewhere above the x-axis. We don't know the y value, so we can just make a random point. But what is important, what they ask us, is to know to clearly show the x, clearly indicate the x coordinates of the turning points. So this is then 1/3 there. We know this is at -1 or -1/3. This one was at 1/2, and this one was at 3. Okay, so that's what we know so far. Now, in this, they also give us the turning point, the second turning point too, because it's decreasing up until that point. So that must be the turning point. So our turning point over here at 2, so let's say it just lies here. Remember, this is just a rough sketch. Okay, so with that given information, we know that the graph must look something like this, where it's going up. This is the first turning point, is coming down, going through that turning point and that x-intercept. So here we have our 3 x-intercepts and we have our 2 turning points and the shape of the graph. Now question 30.1. If g is a cubic function, then we also know the cubic function tells us that the graph would either look like this or it would look like that. Then g, 3 equals to g, the first derivative of g at 3 equals to 0. So what this tells us over here is that, first of all, it tells us that g of x, g at 3 is equal to 0, and g, the first derivative at 3, is equal to 0. So this would then tell us that the x-intercept, so there we have x-intercept, and x-intercept is at x equals to 3. So if I draw that graph, let's just put that here. All right. We have the, let's say 1, 2, 3, and here 1, 2, and 3. Okay, so we know that this is one of our x-intercepts. We also know that the first derivative at 3, so a turning point is also at x equals to 3. So this is also a turning point. We just don't know yet, is it going down or where it actually lies. We just know that that's where a turning point is. Okay, so that's all that the first piece of information tells us. The next one tells us that g0 is 27. So if I make my x0, I get my y-intercept. So that means my y-intercept is at y equals to 27. So let's say we've got y-intercept there at 27. And then it says that the second derivative is greater than 0 when x is less than 0, and the second derivative is less than 0 when x is greater than 3. So now we just need to establish what is this actually telling us. When the second derivative is greater than 0, what does that mean? That means concave up. Okay? And when the second derivative is less than 0, that means concave down. Okay, so that means concave up looks like this, concave down looks like that. So this is actually telling us what the form looks like. So if it is concave up, where x is less than 0, that means this side of the graph it's concave up, this side of the graph it's concave down, where x is greater than 3. So if I compare these two to what we've just read here, this guy is concave up on this side and concave down on that side. So this is then the general form of my graph. Now once again, then they say draw a sketch of G indicating all the relevant points. Okay, so meaning if I go from negative, if I go back from 0 and then 3, so if this guy is then going to be concave down, we can say the turning point is going through there, and then we actually don't have much information about at -3 that the other turning point. We just know that the graph is going through there. And this is about all we know, because this is the x-intercept, and it is also, so this is about all we can sketch. It can look slightly different, but we know that the turning point and the intercepts need to be at the same point. So that means the turning point needs to be here at this point, but this, we don't have any information about this turning point, so that can go down. But this, it has to go through this where y equals to 27. So if those things are in place, then this is a rough sketch of these pieces of information. So question 30.2, the function g has the following properties, where g at -2 is equal to g at 4. What does this tell us? This gives us our intercepts. So that means that our x-intercepts will be at x equals to -2 and at x equals to 4. Right, then the graph for g, the first derivative is concave up. Now, when we look at the graph of the first derivative, if I have a graph, a cubic graph, and I find the first derivative, the graph of the first derivative is a quadratic graph. Always, the first derivative of a cubic function is a quadratic function. So it can either look like this or this. Now, in here they say the graph of the first derivative is concave up, meaning the graph of this is what the first derivative of our function would look like. Then the graph of the first derivative has x-intercepts at x equals to 0 and x equals to 4 and a turning point at 2, at x equals to 2. Okay, so let's actually now just draw that a bit better. It looks like this. It's concave up, and its x-intercepts are at 4, or at 0 and at 4, and its turning point here is at x equals to 2. Now, what does these points tell us? We know that if we put the first derivative, because remember this is now our graph of the first derivative, right? And if we put our first derivative equal to 0 and solve, that is this intercepts that we're actually solving for. And the first derivative tells us where our turning points are. So this then for our original graph will be our turning points. So we know that our turning points are at x equal to 0 and at x equals to 4. All right, and then that's all the information they give us. Okay, so let's use this information and then see if we can sketch this graph. If I draw it like here and here, we have that our x-intercepts are at -2 and 4. So let's draw 1, 2, and then 1, 2, 3, 4. So this is where my one intercept is, and that's where my other intercept is. Okay, turning points. So turning points are at 0 and 4. So this is a turning point over here, and we don't know, well, we're going to use this piece of information to find out what shape it is. So remember our two shapes, we've got this shape or this shape, okay? And here we already now know our turning points is at, let's just draw this. We know this one turning point is at 0 and the other turning point is at 4. So, or it could look like this, where our one turning point is at 0 and our other turning point is at 4. Now, if we look at this, the first derivative is also the gradient, meaning if our first derivative function is positive, it means that my original function is going up, or has a positive slope. Then it's got, now my first derivative becomes negative, meaning my original function has a negative slope, and then it becomes positive again. So if I analyze this using this one, if I'm going from less than 0 up until 0, I'm moving upwards, meaning I've got a positive slope. Then crossing 0, I'm going down, meaning I've got a negative slope, and then positive again. So that actually fits this description where we have, before we get to 0, we're going, we've got a positive we have positive, where my y value is positive, meaning my original graph is going up. My first derivatives graph has a positive y value, then a negative y value, then a positive y value. So this one has a positive gradient, negative gradient, positive gradient. So this is actually the form that we're going with. So we know that we have a turning point here, and we have a turning point at 4 as well. So its intercept is at 4 and its turning point is at 4. Okay, so that means then let's lift this turning point up a little bit, because the graph is now, look, it's going up first. It's going up first, and then it's coming down, but then the turning point and the x-intercept is here. So this is going down and then turning here again. Okay, so that's a very general what this graph would then look like. Right, and then we are finally done.